Hello, I'm Gabrielle Taylor. I'm going to be doing homework 3, part A. So we have a distillation column, and it has 13 stages, and we have a reboiler and condenser. And we want to find out the molar holdup of this distillation column, pretty much. And we want to figure out the feed composition as this goes through the distillation process as well. So let's draw out what our distillation column is going to look like and kind of just very basics of it. So each one of these squares is a tray, and in the middle you're going to have a feed, so this will be your feed stage, and in between these stages this is separating a vapor and a liquid, right? So your vapors are going up and your liquids are going down, and so here you have your vapor going up and your liquid going down, and it's going to be the same throughout all of it. And pretty much what you have is down here we have our reboiler, and down here we have our condenser. So through this we can tell that we have, so something's important to note about this. Oh, and we have a distillate leaving here and a bottom's leaving here. So some important things is, so this bottom part here, we can see that liquid is not exiting and going back into the distillation column here. And we can see that vapor is leaving the system but not coming back or entering. You know what I mean? And also this stage here, we don't have a liquid entering either. And down here, we don't have a vapor entering either. So these things are going to be things that we have to consider when we are doing our equation on Excel, on Python. So what also do we need to look at? So we have a molar holdup. So let's kind of draw this. So this is kind of our tray, and you have some sort of mole, like this is our liquid, right? And you have some vapors coming through it, and the vapors there. But a molar holdup is the height, and this is called here, is your weir, right here, W-I-E-R. That is your weir on the tray. But the height that's past this weir here, past that wall size, this right here is called your molar holdup. And so depending on the height of that wall is going to have a different composition of your weir, of your composition of your flow rates and your compounds and your liquid and your vapors. So it's very important. So this height here as well. So the molar holdup, and what we need to know about that is we have the Faraday, we have the Francis Weir constant, or Weir formula, and this is going to give us the Weir constant, and we can use that to figure out this molar holdup as well. So we can go to our coding portion. This part, I have this imports, so we have our imports, and then this is what we were given from the problem statement. So I can just go over this real quick. So we have n is equal to 13 stages. Our feed is what the feed stage is coming in at, which is 7. We have our alpha, which is our relative volatility, which is 2. We have our feed rate, which is 1 moles per second. We have Z, which is our molar fraction of the more volatile component, which is 0.5. And we have Q, which is the mole fraction of the liquid phase coming in at the feed. And then we have our reflux ratio. Another thing important to know is the reflux ratio is the part of the liquid coming from the condenser and going down. And then that is a ratio between what is leaving through the distillate. So that's important to know. And then we have our holdup at the tray is 0.2, the holdup at the boiler, the reboiler is 0.5, and the holdup of the condenser is 0.5. So the first thing that we want to do is, let's do our holdup not. So our holdup at the steady state. So we're pretty much just going to do mp.r, and we're going to fill this up. So we have our holdup. So we just wanted to combine these two, so we just have something that by 15 by 15, instead of keeping it the way it is. So condenser comes first. It's the top of the reboiler, and then we're going to have trays. We have 13 trays, so we're going to have to multiply this by 13. So, hold up. Not. And you need to do a comma here because it's going to just multiply by 3, and you don't want to do that. You want to multiply, well, it's multiplied by 13, but you don't want to do that. You want to make it 3 separate cases. And then hold up at not underscore boil, so your boiler. Okay. And then we want something to fill our initial of what's going to be changing, which is our holdup, right? Just our holdup is going to equal mp dot full well, let's do mp dot zeros. Just fill it up with zeros for now, and n plus 2, and that's for the reboiler and the condenser, right? So this is good for now. So now let's do our right-hand side rule. So defining our right-hand side, we want to do t in our vector. So the first thing that we want to do with this is our vector is, we're trying to figure out the mole composition for this. So m is our moles and our vector is here. So we want to find them, the difference, the m difference between these, and we'll do m minus our holdup not. So the original steady state minus what our mole holdup is going to be currently, and that will be our m difference. And so then from that, we can do is we can use this difference and the Faraday constant to come up with L. So we have L, and that's going to be equal to, so our liquid flow rate inside is going to be equal to, and I forgot a weir constant. Our weir constant is going to be equal to 0.1. And then here we have it as the weir underscore constant times mp dot weir. So what we want is m diff to be, if m diff is less than 0, we want it to be 0, and then if not, it's going to be the m difference. So we're not multiplying by anything that's negative. And then what we know about our L is that we have our distillate and our reflux ratio. We know our distillate is equal to our L not divided by our reflux ratio plus 1. And we know that our L naught is going to be equal to our D divided by R. R divided by D. R divided by D. And then from this, what else do we have? Then we can do our dm. So our dm, we could start it off with np dot zeros for n plus 2 again, and we have our dm. So we have a problem with code. So this is supposed to be full np dot that, and then we are starting with our initial as 10 moles at each holdup. So that is something that's good to know. And then if we look here, this, we're going to multiply this to get it over, so it's multiplying, not dividing. So we have our np dot zeros. Now we want to do is, again, when we were talking about our distillation column, we said that first we want to subtract by our L. And then we want a dm, and we want to subtract by our d, but at the 0 stage, because that's where our distillate at the 0, because that's where it's leaving, right? So the next one we have is dm of -1 is equal to, now we have our liquid. This one, it should be like this, because it's the first stage. The distillate doesn't have that, because it's not that on there. So then we have to think about what is happening on the first stage. So we need to cancel out. We have our liquid here. Liquid at the this -1. Okay, so what this is pretty much saying is we have our dm 1, so liquid is not entering the first stage, so we're disaccounting for that, and we're adding the liquid, but the liquid is leaving on the last stage, so that can't be accounted for because that's going to our bottom in our reboiler, right? So you have to have a -1 there. So after that, we're doing dm, and now we need to do our feed stage. So feed n, and this one is going to be add equal to L, and then this one here is going to be, actually it's not going to be L, it's just going to be F, because it's our feed. I think that will work out. So then we return dm. Okay, so if we think about this, all we're doing is really just thinking about our liquid stages and not our vapor stages. And we need to focus on our vapor stages, so let's put it in between here. So we have our desired distillate set point. We'll say it's that. 0.5 times our F, right? So it's times our F. So then we need to do our vapor on the stripping section, right? So strip is equal to our desired set point plus our desired set point times our reflux ratio minus by our F. And again, this is our vapor, so when our feed stage is coming in, it has two fractions of either a liquid or a vapor component. And so its Q is what our liquid flow rate is, so we have to do 1 minus Q to get our vapor mole fraction. So we can do that. And then we have a rectifying section. It's equal to our V stripping section plus, and then we're going to be adding this again. Okay, and then we want to just make a V is equal to mp dot r underscore And so from here we have our rectifying section first. Well, do we want, no, we want zeros first, because there should be vapor leaving is going to be our what's leaving, so it's not going to have that there. So then we want our rectifying section, which is going to be in between. So rectifying, and then a comma, and then here, so that means we're going to be multiplying it by our feed n, so this is going to give us 7 stages of that. And then we have is our stripping section, so v underscore strip. And we are also going to do the same thing with that. So one important thing about this is that when you have, when you're making these, we can see that we're doing 13 and then we're adding 2 stages for the reboiler and condenser, so you have to make sure that these are at 15. So this is 1, this is 7, so we're going to have to do n minus our feed, right? So that will give us 13 minus 7. So then we'll have the remainder, and then we have to add 1 stage for our reboiler at the end for this one. So float. We need to multiply here and multiply here. Okay, so after this, we need to add it to our molar, because now we talked about it. So this one we're going to start with -1 is going to be to minus equal of our vapor at the 1 stage, because we need to subtract it because vapor is leaving at that stage, and then dm of 1. Okay, then our vapor will be the same. There you go. Okay, let's see if there's any, I don't think there's any mistakes. So next we can go on to making our graph. So we have Tn is equal to 100, and then we want to do is let's do res equal to sp dot integrate dot solve underscore IVP. Then you have your right hand side. This is going from 0 to Tn. And then from that we have our fold up. And then from our hold up, that will be our initialized, because that's what we have initially. And then we have our method is equal to Hw3A and our name, our dense output is going to be equal to 2. Okay, so next thing is we need to make our t-plot is equal to mp dot line space of 0 to t end and 0 to t end, and let's do 200 splits there. Okay, and then so after we have our t end, now we want to do is, so we are going to be simulating our moles, just our moles for this molar hold up. So we want to do res dot solution, and we're going to be solving it using our time plot. And then, so after this, so after we have our plots, we should be ready to make our figure. So fig equals make underscore subplots. And then, so then after that, we have 4i. So then this is where you get something that's different. So we do 4i, and then you're going to put is, so we have our solution here as m underscore sims. We want to put it as m underscore sim, right, in, and then we want to enumerate this. And then in parentheses, we have to put m, or solution, which is m underscore sims. So it's sim, and then it's sims. Yeah. Oh. Enumerate. Oh, I spelled that wrong. Enumerate. Okay, and then so after this, what we want to do is do our fig.add_scatter. And so your x is going to equal your t-plot. And then your y is going to equal the sim, not the sims. If it's a sims, it's not going to show over time. So it's really important to do the sim. So msim. And then name equal to f. Oh. Okay, and then we can do a fig dot update underscore layout width to 600, no, 800. Height is equal to 500. Okay, let's see what this does. No, that's not correct. So this looks like this is working. So we're having problems with probably these equations over. Okay, so I think the problem is here. These should be flipped around. Okay, let's see if that does anything. Doesn't really do anything. Okay, so the problem was I forgot to do this to the exponent for our L, which is our real constant, and this is where we wanted to multiply it by our m difference. So that's pretty big. So this is what it looks like. So these are our molar composition throughout the stages throughout our time, right? So we can see that this is our 14th stage, so our last stage. With the reboiler, you can see that it's coming up, and we're having a composition of 3. Yeah, 3 here. 4 here for stage 6, and these are going to be our rectifying section. Is going to be that. Our 0 stage is where our condenser is, and that's going to be about 6.5. And then our other section, so our bottom half, is going to have around 7. So that is just for the molar composition, and now we have to do the volatility. So we're doing the relative volatility for part A. So after we just did the molar composition and the molar holdup of this, now we need to do the more volatile component. So what we know is that alpha is equal to K1 over K2. Alpha is a relative volatility. We have that given to us. So we also know that this is y1 over x1 is multiplied by x2 over y2. And then we can, from that, we can extrapolate that y1 is equal to y1 parentheses 1 minus x1. And then we have x1 y minus 1 minus y1. So from that, we can distribute out those factors. So alpha is going to be equal to y1 m minus, well, take out the ones because they're all ones, so that's okay. So this is going to equal y minus xy over x minus xy. So what we need to find is we are going to be looking at our x. We're solving for our dx in this, right? Because that's going to be the liquid of the volatile component. But we need to know what our y is for this. So we already have our relative volatility. We are looking for our x, so we need to solve for our y. So from that, we have our, and I'm going to distribute out this alpha. So it's going to be alpha x minus alpha xy is equal to y minus xy. And then I'm going to move over because we're going to pull out that y and solve for it. So it's going to be alpha x. And then this is going to be y minus xy plus alpha xy. Pull out the y, so alpha x is equal to y minus x plus alpha x. And then we'll have y is equal to alpha x over 1 minus x plus alpha x. So this is what we're going to use in our coding. So this is very important. And then one more thing before we start coding this is that we need to know, so we have pretty much, so we're solving, our first one we solve for dm, which is our molar. Now we need our dx, right? We have dmx, pretty much. That is what we're going to be able to find out with our coding. So we can do an equation to solve for dx, and so then we'll have two graphs of dx and dm. So with that, so dmx is equal to x times dm plus m times dx. So we're going to solve for dx. So when we get this, it will be dx is equal to, I'm just going to rearrange these, and it's going to be dmx minus x dm all over m. So these two equations are going to be important for our coding portion. So let's go there. So here is the code that we used originally, right? So this is our, what we have. So the first thing that we want to do is, so we have right now, you know, when we had our initialize as our holdout, right? We need to do the same thing for x. So we could do np.full for this. And we have n plus 2 because, again, we have to have those two stages, reboiler and condenser. And then our guess is going to be our z, right? Because this is the mole fraction of the more volatile component. So we need our z in there. Okay? So Control Z. So next thing that we need to do is, so our vectors, right? So our vector originally was just m. Now we need to have x. So let's take out that x there. And so what to do with this, you need to do an np.split. We are going to split up this vector here. And we want to do 2, and it like that. Okay. So the next thing that we have after this, right? So we have our x. Now we need to solve for our y for when we pull it in to our equations. So our y, what we solved for, we had it as a, or alpha, times x, which we now have initialized. And then we have 1 minus x plus a, which is our alpha, times our x. So that is that equation. So after this, all of this other stuff is correct, but we do have to add down here this. So it's going to be practically the same as the dm, but we're going to change this to dmx. So we'll change all of these to dmx. Okay, so what we want to do with this is now we are going to multiply this by x, And this one we're going to multiply by x at the first stage. And then here we're going to multiply x by the same stage as the liquid. So then our feed composition is going to be Z, right? So that is going to be the mole fraction up there, okay? And so then here, this is where we get into our y's, because the other ones were liquid, so we used x. Now we're using y. So y, and then we want to do the same thing as our v, because they are both vapors. So y, 1. Okay. So now after this, we have this. We're going to return is r.r, and we're going to concatenate this. So, oh wait, I forgot. This is what we need. We need our dmx. Now we need to solve for our dmx, which we already have. So that equation was, I have it on my iPad, so I'll just look it up on there. So we have dmx minus x times dm, and then we are going to divide by m, right? Okay, now after that we can do is our dx minus our dm. And this is good because, again, we want to keep, a very important thing to this is you want to keep the x and the m in the same position where you're setting your vectors. So that's very important. So we can Control C, and now we can go to our plots. So for our plots for this, we have a holdup. So our holdup is going to be np dot r, and then you have holdup. So holdup is not first because that's our m, so it has to be our x. And let's just check to see if this is the initial function I had up here. It is, so that's correct. Okay? And so we have our t-plot, all of that. This t-plot's correct. Next thing that we want to do is Control Z. Okay, so the next thing that we want to do is so the next thing that we want to do is we have our x plot for this. So we have to do x plot msims, and from that we have to do is a split again. So we have to do mp dot split because we need to split them to do a resolution, to do a solve of that. And we need to do 2. And then our axis has to equal 0 because we need to split them so that we don't have any errors, because we might be given some errors that are a little off if we don't have this axis 0. So this is very important to have. You might not have correct results if you have this. Okay, so now we have, I'm going to put this as x plots with an s because we're about to enumerate this, right? So let's copy and paste this here. So we have, I'm going to put this as, this is the last one, right? So I'm going to do x plot. And then this one is going to be x plots with an s. And then this one down here has to change to x plot, not with s. And then I'm going to change this to 1,000 just so we can get a better height on that. Better width on that. Okay, let's see if it does correctly. Well, okay, so what we need to do is we're going to split these up into 2 different graphs. So we have rows equal 1, and then columns equal 2. Okay, so let's get these on 2 separate plots. So this one here is going to be row 1, row equal 1, column equal 1. And then this one here is going to be row equal 1, column equal 2. Okay, so this is what we want. Great. So again, we have this stage over here, which is our M, and now we have our X component of our more volatile. So this is good to see that. So we have stage 0. We can see that our more volatile component is going to have a higher ratio at the 0 stage, which is good because we probably want to distillate. We want to distillate the more volatile component, put that as our distillate. So it's good that we have a bigger mole fraction going up to 90, like 0.9, as our coming out at our condenser. And then this one is our reboiler stage, right? So this is good here because it is going down pretty low. So we're having a good separation between what is leaving in our bottoms and what is keeping there. So that's pretty good. So the next thing that we need to do is a McCabe-Thiele graph. So that will be the next on this part A. So we are going to do the McCabe-Thiele on this. So we have this here. One thing I fixed before this is this 200 here, and I will show you why. I changed this to 200. I don't know if that does anything particular, but we can look together. So res dot y equals shape. Sorry, res dot y dot shape. So let's look at the shape of pretty much our data set points of our res solution. So we have 30. 30 is going to be half of 1 is going to be x, 1 is going to be m. 30 itself is going to be half and half of both of them, right? And then we have our y, is going to be 17. So that is what the res solution chose. 17 is important here. So I got it to be 17. If I did 100, it would be 15. So that's important to know. Whatever number you put as Tn will change the number of your y itself. So continuing from this, so we want to do a McCabe-Thiele graph. So McCabe-Thiele starts off with, if you know, we're doing steps. So steps is when you're doing a y across, so you start here, start at the same point, and you go over and down, over and down, over and down, right? So your y's are going to be equal at one point, your x's are going to be equal at one point as well. So that's good to know. We're starting first with the y's equaling each other. So let's continue. So the first thing that we want to do is we want to split this. So np.split is equal to, we want to do is the res dot y, and we want to split the first one into 2. Let's see if that works. So why this doesn't work is because 1, we want to split the last one of it. So we have to put a comma here, -1. We want to get the last one because we are going to repeat the first one. Good. See, this is what our distillation is right here. So then after this, we're going to split this up into, so when this splits up to it, it's going to be XS and MS. So our moles and our X's. Remember, X goes first, M goes second. So that's something that you have to keep in continuity with each other. So after this, then we want to solve for our Y, because that is our next step in this. So YS. So YS is going to be like the same equation that we already did. So alpha times, and then instead of our X normally, it's XS, and then 1 minus XS plus alpha times XS, right? So then after this, what do we do? So we have our X's and our Y's, and now it's time to make our McCabe-Thiele plots. So our X of our McCabe-Thiele is going to equal MP.R concatenate, right? And so from this, we want to repeat our XS 0. We want to repeat the first of that, which is our distillate, and then we want to do MP.repeat, and then this is MP.repeat, and in that, we want to do XS and we want to repeat the in between. So we're going to repeat that, and we want to repeat that twice. So this is going to have repeating the in between of those two sections, and then we have the twice amount of times. And then inside here, so we want to have our -1, so our final solution to that. So after this, now we have our McCabe-Thiele. So our McCabe-Thiele we're going to have is our concatenate, and then we are going to use, instead of that, we are going to have is, we need to repeat the first one again, right? So it needs to go one and then the same, because we're doing a straight line cross. So what we need to do is repeat, and then we're going to repeat YS, and then we want to repeat the first one. So then 2. And then YS, I think that's it. Okay, now let's check. McCabe-Thiele? Okay, this is good. So we can see here, it's starting out with our initial distillate, right? That's like the final one, and then it's repeating, and then these two are repeating, these two are repeating, these two are repeating. Great, that's what we like to see. So then our M and C. So these two are the same, these two are the same, these two are the same. Yep. And it's starting with this one as that. So that's good. So now we can do our make subplots next. So fig equals make underscore subplots. Okay, and then after this, we want to do our equilibrium. So when we do a McCabe-Thiele, our McCabe-Thiele steps go on an equilibrium curve. And that equilibrium curve is always from a 0 to 1 to 0 to 1, from our x-axis and our y-axis as well. So we need to do let's do x equilibrium. And that's going to be equal to np dot line space, and we're going to do from 0 to 1, and we're doing 100 points in between. And then again, we know what our y is because we saw for y. So instead of using, again, any other one, we're going to be doing the x equilibrium. And then we do 1 minus x equilibrium plus alpha times x equilibrium. Okay, and then after this, now we can do our figures. So fig dot add underscore scatter, x is equal to x equilibrium, y is equal to y equilibrium, and then mode is going to be lines, because this is a equilibrium line or equilibrium curve. And then we can do our figure. Now we can add our McCabe-Thiele steps. So x is going to equal x underscore McCabe-Thiele, and then y is going to equal y McCabe-Thiele. Model is going to equal lines as well. So let's see what this does. There you go. Okay, great. So this is our equilibrium line. It's our blue one, right? And that's going up. It's going from 1 to 1 to 0 down here. So that's great. And then we can see that our stairs are touching the equilibrium line and doing kind of that. So that's good. Now let's see if we put in our line that goes from 0 to 0 to 1 to 1. So if we do fig dot add underscore scatter, and we do x is equal to 0 to 1, and y is equal to 0 to 1, and then we do mode is equal to lines. Okay, great. so this is good because our steps are inside this line here that is our straight line from 0 to 0 to 1 to 1. So that is the end of homework